Welcome, everyone. Today, we are focusing on a critical phase of machine learning operations, automating hyperparameter tuning. If you want to move from manually guessing model configurations to systematically discovering the best performing models, let's get started. Let's start at the foundation. What are hyperparameters? When we train a machine learning model, the algorithm learns certain values from the data itself. These are parameters, like the weights in a neural network. However, hyperparameters are entirely different. These are the configuration dials and switches that you, the engineer, must set before training even begins. Think of the algorithm as the engine and the data as the fuel. Hyperparameters are how you tune that engine. The basics include settings like learning rate or batch size. Why do they matter so much? Because adjusting these dials directly determines if your model learns effectively or if it overfits and fails on new data. The challenge, and our deep dive focus, is that finding the perfect combination manually is incredibly tedious. You are dealing with a multidimensional puzzle. That is why we must move away from manual guessing and start automating this process. Take a look at this flowchart representing the model training process. On the left, we have our three core inputs. We feed our chosen machine learning algorithm and our training data into the central training process. But notice the third input highlighted in orange, the hyperparameters. This is the only input we are actively tweaking to change how the algorithm learns from the data. The training process outputs a trained model, which is then measured against an evaluation metric, like accuracy or AUC. If the metric is poor, we have to change the hyperparameters and run this entire flow again. Our goal today is to automate this loop completely. To solve the manual tuning problem, Azure Machine Learning introduces the concept of a sweep job. What exactly is it? A sweep job is an automated orchestration mechanism that tests multiple hyperparameter combinations for you. The basics are simple. Instead of sitting at your desk running a script, changing a value and running it again, you submit one master sweep job. This job automatically spins up multiple trials, which are just individual training runs concurrently. Why is this revolutionary? It compresses weeks of manual trial and error into hours of automated, parallel computation. How does it work? You provide a single base training script, and the sweep job engine dynamically injects different hyperparameter configurations into each trial. As a deep dive, you don't even have to dig through the results manually. The sweep engine monitors the evaluation metrics logging from every single trial and automatically highlights the absolute best performing model, ready for you to register and deploy. This diagram beautifully illustrates the power of a sweep job. At the top, you submit the master sweep job to the Azure ML Compute cluster. The orchestrator takes over and fans out the workload into parallel runs, represented by Trial 1, Trial 2, and Trial 3. Notice how each trial is testing a distinct hyperparameter, in this case, different batch sizes. As these models train, they all push their results down into the log target metric node. Finally, the orchestrator evaluates all these disparate trials simultaneously and outputs the single best performing model. You are letting the cloud do the heavy lifting of experimentation. Before you can run a sweep job, you must tell it where to look. This is called defining the search space. What is a search space? It is the strict boundary of acceptable values you want the engine to test. The basics involve classifying your hyperparameters into two types, discrete and continuous. Discrete parameters have specific, hard choices, like a batch size of 16, 32, or 64. Continuous parameters can be any number within a range, like a regularization rate between 0.1 and 0.9. Why do we define this? Because if you give the AI infinite possibilities, it will waste your entire compute budget exploring useless configurations. How do you set it up? You use programmatic classes in your configuration, such as choice for discrete arrays or uniform for a continuous scale. Let's deep dive into an advanced tactic, log uniform. For parameters like learning rate, stepping linearly from 0.001 to 0.002 isn't helpful. A log uniform search space explores orders of magnitude, allowing the engine to efficiently discover the difference between a 0.001 rate and a 0.1 rate. Looking at this tree diagram, we can visualize how to architect our search space. From the root node, we branch into our two main categories, discrete values on the left and continuous values on the right. Under discrete, we use functions like choice to force the sweep job to pick from an exact list, like 16, 32, or 64. Under continuous, we define boundaries. The uniform node allows the engine to pick absolutely any decimal value between 0.1 and 1.0. The log uniform node is specialized for finding optimal scales, jumping through magnitudes. By mapping out your parameters like this before configuring your job, you tightly constrain the compute and guarantee highly efficient experimentation. Now that we have a search space, how does the sweep job decide which specific numbers to pick? This is controlled by the sampling method. What is it? It's the mathematical logic governing the selection process. The basics give us three primary options: grid, random, and Bayesian. Why does your choice here matter? Because it dictates the trade-off between absolute thoroughness and your cloud compute bill. How do they differ? Grid sampling is exhaustive. It tries every single possible combination. It is highly accurate, but terribly expensive and only works on discrete values. Random sampling simply picks random combinations from your space. For our deep dive, I always recommend starting with random sampling. Why? It sounds counterintuitive, but randomly exploring a large dimensional space actually finds optimal models faster than a rigid grid. Furthermore, random sampling supports both discrete and continuous values, and crucially, it supports early termination policies to save you money. It is the perfect balance for initial exploration. This flow outlines your three sampling strategies. On the top path, grid sampling leads to an exhaustive but highly expensive search, and as the dotted line shows, it is restricted to only discrete values. The middle path, random sampling, is exploratory and highly cost-effective, easily handling a mix of parameter types. The bottom path introduces Bayesian sampling, which we will focus on next. It is labeled intelligent and sequential. By visualizing these three options, you can align your sampling choice with your project's specific budget and timeline constraints. Let's take a deep dive into the most sophisticated option, Bayesian sampling. What makes it special? Bayesian sampling is intelligent. It uses the results of previous trials to mathematically dictate what values it should test next. At a basic level, it builds a probability model of your target metric. Why is this so powerful? Because it actively learns. If it notices that a high learning rate causes the accuracy to plummet, it will completely avoid that area of the search space in future trials, converging on the optimal peak much faster. How does it execute this? It requires sequential running. Because Trial 5 needs to learn from Trial 4, you cannot run 100 trials in parallel right away. Here is a senior-level deep dive strategy. Never start with Bayesian. Start with random sampling to broadly explore the vast search space cheaply. Once you find a promising general area, initiate a second sweep job using Bayesian sampling tightly constrained around that area to pinpoint the absolute best possible model. This sequence diagram demonstrates the learning nature of Bayesian sampling. The sweep engine sends configuration A to the trial, which returns a poor 60% accuracy. The engine tries configuration B and gets 85%. Now, look at the self-referencing arrow on the engine, update probability model. The engine actively learns that configurations similar to B are better. Therefore, for Trial 3, it intelligently selects configuration C, which is mathematically near B and achieves a 92% accuracy. It sequentially climbs the hill of optimization, rather than guessing blindly. We've discussed finding the best model, but what about saving money? That brings us to early termination. What is an early termination policy? It is an automated rule that actively monitors your trials and forcibly cancels poorly performing ones before they finish running. The basics are logical. The engine evaluates a trial's metric at specific intervals and compares it to the best trial found so far. Why is this critical? Training complex models takes hours and costs real money. If a hyperparameter combination is clearly failing halfway through, letting it finish is a total waste of your compute budget. How do we configure this? We use policies like bandit, which terminates a run if it falls outside a specific mathematical slack factor compared to the leader. Or median stopping, which kills any run performing worse than the median. For our deep dive, remember this architectural constraint. Bayesian sampling actively learns from poor runs, so you cannot use early termination with it. Early termination is designed exclusively to make random sampling incredibly cost-efficient. Follow the logic in this flowchart to understand early termination. A specific trial is running. It hits the designated evaluation interval, say, epoch 10. The system asks a critical question: is this trial's accuracy within our allowed bandit slack factor compared to the best run? If yes, it continues training. If no, meaning it is performing terribly, the system takes the bottom path and terminates the trial early. This immediately frees up the compute node for a new trial, saving both cost and time. It is aggressive, automated cost control. To make all this automation work, your actual Python code needs to be prepared. Let's look at the training script. What is it? It is the core logic executed by the nodes during each trial. The basics require you to modify your script so it can dynamically accept hyperparameters from the sweep job. Why? Because the sweep orchestrator is injecting different values every time, and it needs a standardized way to read the final score to judge if the trial was successful. How do you do this? First, you use Python's rparse library to catch the incoming parameters, like learning rate. Second, and most importantly, you must use MFlow to log your target metric, such as mlflow.log metric, accuracy, score. Deep diving into this, MLflow is natively integrated into Azure ML workspaces. By explicitly logging your primary metric with MFlow, you are sending a signal back up to the sweep orchestrator, giving it the exact data it needs to rank all the trials and crown the winning model. This diagram illustrates the critical feedback loop between your code and the sweep orchestrator. On the left, the sweep orchestrator starts a trial by injecting a parameter, like learning rate 0.05. The Python script uses rparse to catch this value and feeds it into the model training loop. Once training is complete, the script calculates the accuracy. Crucially, the script uses mflow.log metric to push that accuracy score into the Azure ML run history. The orchestrator pulls that score from the history to evaluate the success of the trial. If you break this loop by forgetting to log the metric, the sweep job cannot function. Let's bring all these concepts together with a real-world use case. Imagine you are a machine learning engineer at Prosware, a healthcare startup. Your team has trained a diabetes classification model that will be consumed by a web app for doctors. The context is high stakes. You must absolutely maximize the model's accuracy, specifically the AUC-weighted metric, but as a startup, you have a strict compute budget. How do you execute this? First, you define a smart search space, using log uniform for the learning rate and discrete choices for batch size. Second, you configure a sweep job using random sampling. Because you chose random, you attach a bandit early termination policy. The outcome is spectacular. The orchestrator evaluates 50 different model configurations in parallel. The bandit policy automatically terminates 20 failing runs early, saving you 40% in compute costs. Within hours, without manual intervention, the sweep job surfaces an optimized, highly accurate model that is immediately ready for production deployment. Our final architecture diagram maps out Prosware's entire optimization strategy. We start with the diabetes dataset feeding into the sweep job configuration. Notice the three pillars of our configuration: the defined search space, random sampling, and the bandit termination policy. These combine to execute 50 parallel trials in the cloud. As execution happens, failing runs are siphoned off and terminated to save money. The successful runs complete, and the orchestrator automatically selects the model with the highest AUC metric. That singular, optimized model is then seamlessly deployed to the medical web app, proving that automated hyperparameter tuning is both highly cost-effective and essential for enterprise-grade AI.